Here's a 4x4 dense complex matrix called F sub 4, the Fourier matrix. Inverting a generic 4x4 takes real work. Gaussian elimination, 16 entries to track. But for this matrix, I can write down the inverse in 5 seconds. It's just 1/4 times the conjugate transpose of F sub 4. No row reduction, no determinants. Why is this inverse essentially free? Let's find out. To see why, we need to understand what powers this matrix. Define omega as e to the 2 pi I over n. This complex number sits on the unit circle at angle 2 pi over n. It's called a primitive nth root of unity, meaning omega to the n equals 1, and n is the smallest such power. For n equals 4, omega equals e to the I pi over 2, which is just I. Now watch the power cycle. Omega to the 0 is 1, omega to the 1 is I, omega squared is -1, omega cubed is -I, and omega to the 4th returns to 1. Geometrically, these 4 powers sit at the corners of a square inscribed in the unit circle. 1 is to the right, I is at the top, -1 is to the left, and the -I is at the bottom. Each multiplication by omega rotates by 90 degrees. For a general n, the powers of omega place n evenly spaced points around the circle. This rich rotational structure is the secret ingredient. The Fourier matrix inherits all of its symmetry from this single number omega. Now let's build the matrix. The Fourier matrix F sub n has its entry in row I, column j equal to omega raised to the power I times j, with the indices running from 0 up to n minus 1. Row 0 and column 0 are all omega to the 0, which is just 1. So the first row and the first column are filled with 1s. The interesting structure lives in the lower right portion of the matrix. For example, take the entry at row 2, column 3. That equals I to the power 2 times 3, which is I to the 6th. Now reduce the exponent modulo 4. 6 mod 4 is 2, so this equals I squared, which is -1. Let's fill in all 16 entries of the 4x4 Fourier matrix. Row 0 is 1, 1, 1, 1. Every entry is omega to the 0. Row 1 is 1, I, -1, -I. The powers of I from 0 up to 3. Row 2 is 1, -1, 1, -1. These come from I to the 0, I squared, I to the 4th, and I to the 6th, all reduce modulo 4. Row 3 is 1, -I, -1, I, the powers 9, 6, 3 reduce around the cycle. There it is, F sub 4. Now look at the second column. It reads 1, I, -1, -I, a full cycle of the 4th roots of unity. The 4th column reads 1, -I, -1, I, the very same cycle, but running backwards. In fact, every column is built from powers of I. So here's the natural question. Are these columns orthogonal to each other? Let's test it by pairing the second column against the 4th. Let's try the ordinary dot product with no conjugation. We multiply entry by entry and add. Take column 2, which is 1, I, -1, -I, and column 4, which is 1, -I, -1, I. First entry, 1 times 1 is 1. Second entry, I times -I, that's -I squared, which equals 1. Third entry, -1 times -1 is 1. Fourth entry, -I times I, that's -I squared again, which is 1. Adding them all up, 1 plus 1 plus 1 plus 1 equals 4. That's definitely not 0. So by the standard real style dot product, these two columns look very much not orthogonal. Something is wrong here. The issue is that the real dot product is the wrong tool for complex vectors. In complex space, we need a different inner product. The Hermitian inner product of U with V is defined as the sum over K of U bar sub K times V sub K. You conjugate the first vector, then multiply entry-wise and sum. Let's redo column 2 with column 4 using this rule. First, conjugate column 2. 1 becomes 1. I becomes -I. -1 stays -1. and negative I becomes I. So the conjugate is 1, negative I, negative 1, I. Now multiply by column 4 entry-wise. 1 times 1 is 1. Negative I times negative II is I squared, which is negative 1. Negative 1 times negative 1 is 1, and I times I is negative 1. Now sum these. 1 minus 1 plus 1 minus 1 equals 0. The Hermitian inner product is 0, so columns 2 and 4 are orthogonal. Now let's check the column length. The square length of any column is the sum of the magnitude squared of its entries. Take column 1. Its squared length equals the magnitude of 1 squared plus the magnitude of I squared plus the magnitude of negative 1 squared plus the magnitude of negative I squared. Each of those magnitudes is 1, so we get 1 plus 1 plus 1 plus 1, which equals 4. The squared length is 4, so the length itself is 2. And the same story holds for every column of F sub 4. Let's package this together. The conjugate transpose of F sub 4 multiplied by F sub 4 computes every column against column Hermitian inner product. On the diagonal, we get each column dotted with itself, which equals 4. Off the diagonal, we have distinct columns which are orthogonal, so those entries equal 0. The result is 4 times the identity matrix. Therefore, F sub 4 inverse equals 1/4 times F sub 4 Hermitian. The inverse falls out for free. Here is the general result. F sub n inverse equals 1 over n times F sub n Hermitian. This holds for every size n because the columns of the DFT matrix are always mutually orthogonal, and each column has squared norm equal to n. So F sub n Hermitian times F sub n equals n times the identity, and the dividing by n gives the inverse. This is exactly why the inverse discrete Fourier transform is just another DFT. You simply flip the sign in the exponent and then multiply by 1 over n. The very same orthogonality is what powers the fast Fourier transform, JPEG image compression, and many partial differential equation solvers. When a matrix is built from roots of unity, linear algebra becomes almost effortless.